If you have ever seen kind of that rainbow sheen on top of a slick of oil and wondered what is that about, where is that coming from? The answer to that is thin film interference, and that's what this video is about. Thin film interference is one of these topics that a lot of times people get kind of a basic understanding of how to use an equation, but don't take the time to figure out just what's going on. So I want to break this into small pieces so that you can understand what's going on, and then we can come back to the equation afterwards. So what I've got is one major consideration, and it is that the phase of a wave inverts when we reflect off a more optically dense medium. So let me see what this looks like, because we haven't spent a whole lot of time talking about phases. We haven't really had to do much with this. If I have a wave that looks like this, I can give this thing some kind of a phase value, and it doesn't really matter what. If I have a copy of this that is running at the exact same time, I could say this one has a phase of 0. And I'm not really talking about its phase, I'm kind of talking about its relative phase. So it has the same relative phase as the first one, which again might not make a whole lot of sense until we look at something that's not that way. For the second or third wave, I suppose, this one is going to have a phase of pi, or 180 degrees. And it is because every time that this bottom wave is on a maximum, the top wave is on a minimum. And every time the top wave's on a maximum, the bottom wave's on a minimum. They have the same wavelength, the same frequency, and everything like that. But when these two waves come into a space together, they will cancel each other out. These will add destructively. Where if I take these top two waves, these would be called in phase with each other. If I take these top two waves, these are going to add constructively. These are considered in phase, and these are considered out of phase. Even that is a little bit misleading, because these don't have to be completely out of phase. I could have a wave that doesn't meet exactly at the opposite, that meets, I don't know, here. So that I've got this one on a 0 when this one's on a maximum, this one's on a minimum when this one's on a 0, that kind of a thing. And those would also be out of phase, just they would have a smaller degree of out of phaseness, if that's okay to say. So this bottom one, we are talking about fully, completely out of phase. They are 180 degrees apart. When they are completely out of phase, we will get a destructive addition, and those waves will cancel each other. So those are kind of the building blocks I need. Now on to thin films. If I have a thin film like this, and I'll draw it real thin first, and then I'll kind of blow it up and look at what's going on. I have these light rays that come in this way, and they bounce off like that. But something happens inside this thin film, and so I get these parallel waves that bounce off. These parallel waves, they can either add up or they can subtract. They can add constructively or destructively. Now for thin film interference, the approximations that we make are one, that this is a thin film, and 2, that our light source is coming in from pretty near vertical, and you'll see why. The big pieces that I'm going to need for this to work are the media we're traveling through. So N1, N2 is the refractive index of the second medium of the film, and then N3, what's underneath. And these actual numbers, N1 and N3's actual numbers don't matter too much. N2 does matter numerically, but the ranking of them, that's really where this is going to come in. So I want to take this space right here and blow that up and look at just what's going on there. I have something like this, and I have up here my N1, in the middle my N2, and on the bottom my N3. I've got this light wave that's coming in this way, and here is a normal. Now this wave that's coming in is going to reflect, and it's going to refract. Anytime we have one, we have the other. And I'm going to need some values for these. I'm going to say this is n equals 1. We'll have this one be maybe oil or gasoline. We'll go at n equals 1.4. And this bottom one can be water, is n equals 1.33. So this is air, gasoline, and water. Now I can talk about phases, and that's fine. We're going to say this thing has a phase of 0, but phases really only have 2 values that we care about. We're not really looking with this stuff at the in-betweens. We are looking at fully in phase or fully out of phase. So there are really only 2 options, a phase of 0 or a phase of pi. If there are only 2 options, I would like to model this as a heads or tails situation. So this thing, this phase of 0, I'm going to call that a heads wave. What I said right from the start was I am going to invert my phase if I am bouncing off of something, off of a medium that has a higher index of refraction. So let's see what that looks like. I'm going to bounce off of this medium, and I am in a medium with an index of 1. I am bouncing off of a medium with an index bigger than 1. Because I'm bouncing off of a higher refractive index, I'm going to pick up an inversion. So I'm bouncing like this. I am picking up an inversion, so this is a 180 degree phase shift. And I change the color, not because the wave is going to change color, just because it's easier to quickly see what's going on, and I'm going to call this a tails wave. So I have 3 identifiers that I'm using here. You don't need to use all 3, just one of them will be fine. But I'm using a heads and tails, I'm using a color coding, blue for heads, purple for tails, and I'm listing off the phase. You pick which one you like. This wave that comes in, it also refracts. So it would have kept going this way, but we're changing media, and we are changing to a higher refractive index, so we are going to have to refract toward the normal. It's a refraction, so there is no phase change or anything like that. There's no way to pick up an inversion from a refraction. It's only upon reflection that it's possible. So that's still a phase of 0, that's still a heads, that's still a blue wave. And here is this second normal. Now, I'm in a medium with a refractive index of 1.4. I'm bouncing off of a medium with a refractive index of 1.3. I'm bouncing off of something with a lower index of refraction, so I don't pick up an inversion. So I reflect off of that. And because I'm going from 1.4 to 1.33, I'm going I'm bouncing off of a lower index of refraction, so I do not pick up an inversion. This is still a phi equals 0 heads wave. This wave will continue. I'm going through water now, so I'm going to refract in here something, but I'm not actually worried about what's going on with that. If I were, it would still be a phase of 0, it would still be a heads wave, but that light wave is gone to me. I don't really need it. I don't have to worry about what happens to it. Now this wave, so this wave is coming up toward the air again. There's my normal. And I am just refracting. I'm not picking up any kind of inversion or anything like that because I am not reflecting. I am refracting. So this is a phase of 0 heads wave. And now I've got the thing that I really need for this thin film interference business. I do want to say I'm going to need the thickness of this film. So there is a thickness. I'm not sure why lowercase t is used there when that's always time, but whatever, so it goes. That's what's always used, so I'm going to stick with it. So what I have is these two outbound waves that are going to be parallel to each other. They're necessarily going to be parallel, but they are out of phase. If these waves were in phase, they would be constructive. We would get constructive interference. These waves are out of phase, so on their own, those waves should be destructive. So we are looking, how do we make them constructive again? And the answer is, we need a path length difference, just like we had with two-slit interference, or even one-slit interference. We need some kind of a path length difference. If the path length difference is equal to a half a wavelength, then this blue wave will have picked up an extra 180 degrees. These will be back in phase and we get constructive interference. If it's equal to 1.5 wavelengths, we get the same. 2.5 wavelengths, we get the same. So what we want this to be j plus a half wavelengths, where j is just any whole number. The way that works out, this top one would be my j equals 0. If I plug that in, this would be my j equals 1. J equals 2. I'm just looking for a path length difference that is something and a half wavelengths. There's a little bit more. The path length difference, that's going to be double the thickness. It's not exactly double the thickness, but if these waves are coming in nearly vertically, then we are nearly. Our path length difference, if this wave were vertical, would be down, and back up would be double the thickness. As this incoming wave gets farther and farther from vertical, so with an incident angle that differs more and more from 0, this approximation becomes worse. We are looking for thin film interference pretty much always near vertical, so that's okay. So we've got double the thickness equals j plus a half times the wavelength. There's more. What we need here, we need the wavelength in that medium. So in the film. And the wavelength in the film is the wavelength in our first one divided by the index of refraction of the film. So it is our incident wavelength divided by the index of refraction of the film. I'll do a couple examples of this in a separate video. For right now, that means I've got double the thickness equals j plus a half times wavelength over n2, or 2 times the thickness times the wavelength of the film, or index of refraction of the film, equals j plus a half times the incident wavelength. That is going to be my equation for constructive interference. For low to high to middle. Or really for N2 is bigger than N3. N2 is bigger than N1. It doesn't really matter how N1 and N3 compare to each other. So why do I have that? Because what happens if I've got a less optically dense medium in between? Let me do that one. I'm going to do a similar setup. But maybe up here I've got air. Let's stick with our gasoline here. And we'll go glass here. So N is 1. N is 1.4. And glass, let's go 1.5. Depending on the type of glass. I have my incident ray that comes in. This is a phase equals 0 Hertz wave. I hit a normal and I reflect. I'm going from n equals 1 off of n equals 1.4, so I'm going off of something with a higher index of refraction, which means I have to invert. So this is a tails wave with a phase of 180 degrees. Let's keep going here. I refracted, so I'm moving through this. I hit another normal, another interface. I'm going to again refract, but I don't care. This was a phase equals 0 Hertz wave still. This is still a phase equals 0 Hertz wave because I can't pick up an inversion by refracting. But now I want to look at this reflection at this surface. I'm in n equals 1.4. I'm bouncing off of n equals 1.5, so I'm bouncing off of something that's more optically dense, which means I am picking up an inversion. This reflected wave had to invert, so it's a 180 degree phase, or pi. It is now a tails wave. Then I come up here, I hit a normal, I've got to refract. This is a tails wave, or 180 degree wave, or pi wave, however you want to say that. Because I'm just refracting, and refracting doesn't pick up any more inversions. So what I have in this case is these two waves, and these are already in phase. Which means if I don't do anything to them, they will add constructively. So now what I need, my path length difference, if that's 0, I get constructive. But a path length difference of 0 means I have a film thickness of 0, and while that does qualify as a thin film, or it does qualify as thin, it doesn't count as a film. If I get just a wavelength, that works out fine. just 2 wavelengths, that works out fine. So if I can get just a whole number of wavelengths, I'm going to get constructive interference. My path length difference is still double the thickness, and this is still the wavelength in the film. So this is still actually my incident wavelength divided by n film, which means 2 thickness n film equals j lambda incident is the formula that I want for constructive. For low to mid to high, meaning my film is the medium one. Back here, my film was the high one, was the high index of refraction. This one I'm doing for my film being the medium index of refraction. I want to summarize. If film equals the high N, then my constructive condition is that double the thickness times the index of refraction of the film equals j plus a half times lambda incident. My destructive, meaning if I shine, I don't know, blue light on this thing, I'm not going to see any blue light coming off of it. 2 times the thickness times the n film is j times lambda incident. And then if my film equals the middle n, then these two switch spots. Then I've got 2 thickness n film equals j lambda incident, and over here 2 thickness n film equals j plus a half lambda incident, where j is just any real number, or any whole number. Almost. It's any whole number for the j plus a half cases, but if I plug in j equals 0 here, that means I've got a thickness of film of 0, and that doesn't work. Mathematically it does, but it doesn't make sense. Same thing there. So I want to be smart. I want to be able to say I can plug in j equals 0 into that guy. I can't plug j equals 0 into that one. I could rewrite the formula in terms of a j minus a half and then just have all the j's be 1, 2, 3, whatever. But this seems to be the way that is easier to remember, and we just have to make sure that we're not getting zeros.